SRM University, Andhra Pradesh, Amaravati was born to offer a unique learning experience, to deliver cutting-edge education, to foster innovation and to create the leaders of tomorrow. Sprawled over 200 acres, the university has been designed by the world-renowned architecture firm Perkins and Will. The lush, green, eco-friendly campus provides a conducive environment to learning and creativity. SRM University, Andhra Pradesh, Amaravati is a multi-stream research university with focus on diverse fields including engineering, medicine, liberal arts and management. It offers a rich selection of graduate and undergraduate programs across faculties. What's more, the faculty is highly qualified, experienced and has global exposure to mentor and support the students every step of the way. In a bid to accomplish research excellence, SRM University, AP Amaravati offers pioneering research under subject experts and thought leaders.
Hi, so this is our computer lab, one of the most modern labs across India. We've been doing so many projects across here, and with the amazing faculty support, you can do wonders here. These are all wonderful modern systems.
Research is an integral part of SRM Amaravati and spans engineering, science and liberal arts. To foster a culture of research excellence, the university integrates research in the undergraduate curriculum through Undergraduate Research Opportunities Program. The university is setting up centers of excellence in areas such as artificial intelligence and machine learning, renewable energy, meta-materials.
This is a place where we work on bleeding and cutting-edge technologies, avoiding time sinks and focusing on innovation. With our work, we have also been awarded the Reimagine Education Silver Award awarded by Wharton School of Business and QS.
50% of our lab members are women. We have also organized events which will foster the spirit of programming in women who have never programmed before.
The university is equipped with a cutting-edge Next-Tech laboratory. It holds the proud distinction of winning the maximum number of hackathons in India. The university is currently working on developing a hydrogen fuel cell-based train. SRM Amaravati's board members comprises of leaders and industry from across the globe. Ensures global exposure for its students by collaborating with some of the world's most eminent universities. MIT US, UC Berkeley College of Engineering, IIT Chicago and EFREI, to name a few. Boasts of excellent infrastructure and resource availability, including AC bus service, round-the-clock ambulance services, bank, ATM, dining area and extensive sports facilities. The hostel boasts of spacious, well-appointed rooms, common balconies, SRM University, Andhra Pradesh, Amaravati was born to offer a unique learning experience, to deliver cutting-edge education, to foster innovation and to create the leaders of tomorrow. Sprawled over 200 acres, the university has been designed by the world-renowned architecture firm Perkins and Will. The lush, green, eco-friendly campus provides a conducive environment to learning and creativity. SRM University, Andhra Pradesh, Amaravati is a multi-stream research university with focus on diverse fields including engineering, medicine, liberal arts and management. It offers a rich selection of graduate and undergraduate programs across faculties. What's more, the faculty is highly qualified, experienced and has global exposure to mentor and support the students every step of the way. In a bid to accomplish research excellence, SRM University, AP Amaravati offers pioneering research under subject experts and thought leaders.
Hi, so this is our computer lab, one of the most modern labs across India. We've been doing so many projects across here, and with the amazing faculty support, you can do wonders here. These are all wonderful modern systems.
Research is an integral part of SRM Amaravati and spans engineering, science and liberal arts. To foster a culture of research excellence, the university integrates research in the undergraduate curriculum through Undergraduate Research Opportunities Program. The university is setting up centers of excellence in areas such as artificial intelligence and machine learning, renewable energy, meta materials.
This is a place where we work on bleeding and cutting edge technologies, avoiding time sinks and focusing on innovation. With our work, we have also been awarded the Reimagine Education Silver Award awarded by Wharton School of Business and QS.
50% of our lab members are women.
Balamulli?
We also organize events.
Hello. Balamulli, can you stop? Yeah.
Yeah. All right.
Yeah,
I am ready.
Yeah. Yes. Actually,
Sure.
we will start in just 1.5 minutes.
No problem.
Yeah. So, Murli, you are ready, Murli?
Yes.
Yeah. So I think in next 60 seconds we can start.
No, Ranjit.
Ah.
1 or 2 minutes you can wait because participants are joining. Maybe you can start at 303 or 305. Still participants are joining, I'm seeing. Yeah.
Yes, sir.
Hello. Sir, మీరు జాయిన్ అవ్వండి సార్. ఓకే ఓకే సార్. ఓకే యా ఓకే సార్. రైట్ సార్. థ్యాంక్ యూ సార్. क्या रंजित शुरू करें या 2-3 मिनट वेट करें?
Sir, we can start because we will take anyhow 3, 4, 5 minutes.
So, okay, let them join.
Almost 250, so it will be reach 400 in 5 minutes.
No, wait. If it is okay for Professor Ajay Sood. Is it okay, sir?
Yeah. Okay. No problem.
Yeah.
I can start whenever you give me a green signal.
Correct.
Sure, no problem.
Okay.
So are your classes on?
Yes, sir.
Yeah, now online classes are going on. We decided to provide online teaching until end of this calendar year.
Okay.
The first
All
semester.
right. So you will take a call when it comes to
Yeah. If things become favorable and conducive, we may start in January the physical classroom teaching.
Okay.
Now our hostels also are not operational. Students take classes from wherever they are.
Okay. That's good. That is safe. Very safe. Okay. So how many students have joined in your university now, undergrad?
By now, we have about 3,100 students.
These are
undergraduates. BTech we offer in computer science, electronics and communication engineering, mechanical engineering, electrical and electronics engineering, civil engineering. Also, we have started courses in basic sciences such as BSc Physics, Chemistry, Biology, and also BBA.
Okay.
BA History.
Excellent.
We call that as School of Liberal Arts.
Okay. And what about masters? You are starting.
Masters this year we are starting.
Okay. Great.
See, we made the first batch admissions in July 2017. About 240 students. Then later on every year about 1,000 students. Now we have admitted the fourth batch.
Excellent.
See, as now the National Education Policy emphatically recommends liberal arts also. 2 years back we started School of Liberal Arts.
Very nice. Very good. No, I think it's a very interesting thing.
Yeah. And the students will choose some courses from liberal arts.
Yeah. No, I think that's very, very interesting aspect.
Yeah.
Absolutely. Good.
Ranjit, in another few seconds.
Yes, sir. I think our VC sir is also joining.
Yeah, he has joined. He told me.
Is this the first lecture you said?
Yes, sir.
It says number 1. I didn't notice this so far.
Yeah.
Oh, okay.
We wanted Professor Ajay Sood to give the first lecture.
No, thank
whatever
you so
date
much.
It is.
No, thank you. I didn't realize this. I just noticed few seconds back. So, yeah. So you would like to have every month or something?
No, maybe 2 in a month. By now, I'll tell you, Professor Balki has agreed.
Okay.
Professor Astosh Sharma has agreed.
Okay.
Then Dr. B.S. Murthy, Director IIT Hyderabad. Then Dr. S. Chandrasekhar, Director IISc Hyderabad.
Yes, correct.
And Professor Basavaya from University of Hyderabad.
Yeah.
Professor Sher Ali. Like that, some 7 or 8. They have agreed, and we are scheduling.
Okay, very nice.
2 lectures in a month.
Okay.
Approximately.
Good. No, that's good.
Of course, we had to avoid these festive days.
Yeah.
Okay,
so we can start, sir.
Yeah.
So, good afternoon, all the participants, and also good afternoon to the speakers. I will request Professor D. Narayan Rao, Pro Vice Chancellor, SRM University AP, to say a few words about the University Distinguished Lecture Series and also to welcome our special guest.
Dear Professor Ajay Kumar Sood, the Vice Chancellor of SR University AP, Professor V.S. Rao Garu, Deans, Directors, and learned faculty members, research scholars, and students, the participants of this lecture. I extend a warm welcome to all of you for the distinguished lecture being given by Professor Ajay Sood. I am glad to know that 1,253 members from different institutions, national laboratories, such as, and then IITs, IISc, and also a few universities from abroad have registered to attend this lecture by Professor Ajay Sood. I deem it a great pleasure and privilege to extend a warm welcome to Professor Ajay Kumar Sood, a well-established and scientist of global repute, known for his pioneering research findings on graphene and nanotechnology. I know Professor Ajay Sood for almost 2 decades, and we have been working jointly on and organized a few programs earlier. Also, he is a well-wisher of SRM University, and he is the chairman of Research Advisory Council of SRM University Chennai, where he mentored many faculty members, including Ranjit Thapa, Vinod, and others. Thus, SRM University has great respect towards Professor Ajay Sood, and also he directs and shows the way how the young researchers need to carry out research. Professor Ajay Sood, a distinguished honorary professor of physics at Indian Institute of Science, Bengaluru, a fellow of the Royal Society, and a great son of India. Let's give a big applause and welcome to Professor Ajay Kumar Sood. Participants, wherever you are sitting, please give a big applause.
Thank you.
SRM University AP has taken the initiative to organize University Distinguished Lecture Series by well-established and eminent scientists from India and abroad for the benefit of students and the faculty members. I am extremely happy that the first lecture of the series is being delivered by Professor Ajay Kumar Sood. You are all aware that in the recent months, doctors, researchers, engineers, and scientists from several fields of knowledge around the world worked together to confront the coronavirus outbreak with an unprecedented spirit of collaboration. A new interdisciplinary collaboration culture is taking root. Scientists, virologists, immunologists, regulators, and industry executives are working together with the sole purpose of developing and manufacturing vaccines for COVID-19. The National Education Policy NEP 2020 strongly advocates and emphasizes that the societal needs of the 21st century require broad-based multidisciplinary research and education. Thus, I'm sure that the lecture, namely Doing Science Without Borders, rightly chosen by Professor Ajay Sood and being delivered now, will be quite interesting and is very timely for inculcating the culture of multidisciplinary research among the students and faculty members. Once again, we are grateful to Professor Ajay Sood for kindly accepting our invitation. Thank you one and all.
Yeah, thank you, Professor D. Narayan Rao. So as we have our Vice Chancellor also in our panelist, so I will request our Vice Chancellor, Professor V.S. Rao, to say a few words.
Professor Sood, it is indeed an honor for this university to have the University Distinguished Lecture Series being inaugurated by an eminent person like you, and that too on a topic about science without borders. I'm sure the entire audience and our university will get immensely benefited by your lecture. So welcome And thank you, sir, for accepting our invitation. Over to you, Ranjit.
Yeah, thank you, sir. So I will just now go through his very small, short introductions about Professor Ajay Sood. So Professor Ajay Sood is a fellow of Royal Society and is a physicist, researcher, and holder of 2 US and 5 Indian patents. He is Year of Science Chair Professor, Department of Physics, Indian Institute of Science, Bangalore. He is also an associate editor of a prestigious journal, ACS Nano, and executive editor of the journal Solid State Communications. He was awarded Santi Swarup Bhatnagar Prize in 1990. So the government of India honored him in 2013 with Padma Shri for his contribution to the field of science and technology. The Third World Academy of Science recognized Professor Ajay Sood contributions towards science and technology, and they awarded him with TWAS Prize in Physics in 2000. Professor Ajay Sood was elected a Fellow of Royal Society in 2015. So he was a pride for us. So Sood effect is well known in physics nowadays. Everyone who is in the nanotechnology area, they knows about Sood effect. So I want to emphasize this Sood effect. So Professor Ajay Sood, through his experiment in 2003, generated electrical signals by passing liquid over solids or through nanotubes. And this phenomena has now termed by scientific world as Sood effect. So this is really also a big achievement, and every researcher wants this type of effect in their own name. So he has also invented an ultra-sensitive immunoassay by subjecting colloids to an electric field, thus generating non-equilibrium phenomena, an invention that has relevance in the medical field. So he has published more than 300 research articles, and the citation received is around 23,587. So his current H index as per Google Scholar is 62. With this short introductions, I will request Professor Ajay Sood to deliver the first university distinguished lecture. And thank you, sir, for accepting our invitation. Over to you, sir.
Thank you very much. I'll start sharing it first and see. Am I able to share it?
Yes, sir. Yes, sir. You can go to full screen.
I'm just doing that. Is it visible now?
Yes, sir. Yes, sir.
Excellent. Okay. Thank you very much. So first, allow me to start thanking Professor D. Narayan Rao for his very kind invitation to have me for this distinguished lecture series, and Professor Thapa for his very kind words, as well as for logistic support. So when Professor Narayan Rao asked me to give this talk, I was not sure what to say, which will cut across various disciplines, because it's a very broad audience. So I decided to take some examples from our recent work, where I thought I'll tell some very exciting science that is going on in our lab, but which also cuts across the conventional boundaries of physics. So I thought it may touch some of the young people what we can do, really looking at the phenomena all around us. So this first slide actually are the videos from our experiments, which I'll exemplify by 3 stories. So this is the target for the next 50 minutes. Okay, so let me say a few words, and it does not need any intelligence to conclude that complex contemporary problems are not amenable to single discipline knowledge domain. And we have seen that discoveries are more likely on the boundaries between fields, where perspective, concepts, and tools can bring new insights. And one example which has really spanned the almost entire science is the influence of big data science, artificial intelligence, on many disciplines, which expands their horizon. Now, in these difficult times of pandemic, as Professor Narayan Rao said, the world is grappling with a really challenge. And there have been now many attempts, or in fact, they are already on, where interdisciplinary research is being used to handle various aspects of this pandemic. So I've just taken two quotes from people because it says that we don't have all the strength in one university. So collaboration between universities will be important in this field, between different disciplines and so on. So what I thought that in my talk today, before I come to it, I wanted to show a example which really motivated me when I was a student. And this is the book, what is called What is Life? Now, the interesting thing is that this book was written in 1944 by an iconic figure in physics, Erwin Schrödinger. We use Schrödinger equation almost every day, and he got the Nobel Prize in 1933. But he wrote this book, The Physical Aspect of the Living Cell. And he introduced the idea of an aperiodic crystal that contained genetic information in its configuration of covalent chemical bonds. Now, this was in 1944, before the discovery of DNA. And this 1950, this idea stimulated enthusiasm for discovering the genetic molecule. So you can see that how a very profound physicist has also made a foray into biological science of a very high-reaching consequence. So this is something very inspiring to all of us, not to be confined to our own discipline, but also encourage us to think beyond. Now, in these three stories which I have taken from my lab, I'll just touch upon them. I will not be able to give all the details, but my goal is to tell you how we can have very excitement, a lot of fun doing basic science, which can have potential applications in the long run. And that has been the guiding principle of my work, that we look for very basic science, but keep our ears and eyes open for possible applications. So this has been very rewarding in the last many years, that we look for a very basic issue, but do not turn away from the application. So three examples which I'll discuss today is the emergent flocking behavior, which you see in nature, but we will do our laboratory experiment to say what is exciting. Second problem is the crystallization of glass. This is a century-old problem, and we will be using machine learning in condensed matter physics, soft condensed matter, to understand this problem. And the third problem, I'll just touch upon, I will not have details, how you can make a heat engine using bacteria. So this is the bacterial nano heat engine. What is the new concept here, and what is our success in this game? So the first story, let me please start. This is really inspired by nature. In nature, we see many phenomena where we see flocking. For example, if you look at bacteria under a microscope, and if they are sufficient in number, they will have a very collective behavior. They will not move individually in an incoherent manner. If you take ants and you go to a forest, you will see that these ants will go around, and this can go on for a long time. This is another example of flocking. And another example which is also seen, if you put locusts, it's a nuisance to have locusts, but if you catch them and put them on a petri dish and watch under in the lab, above a certain concentration, they also show cooperative behavior. And not far behind, these animals also show collective behavior when they are sufficient in number. So this is the behavior you will see in heavy metal concerts or on the or on Indian scene and other context. And this is again a collective behavior of human beings in many situations. So what you would like to see is a flocking is a collective motion of, for example, living organisms in the examples I gave, by sensing each other's presence, orientation and direction of movement. But what is most important here is that it is an emergent behavior which I will show arises from simple rules followed by individuals. So in this collective behavior, there is no central coordination. So there is no vice chancellor here who is dictating what to do. Everything is being done by the participants themselves, and they collectively have this behavior. So this is very important, that it is arising from simple rules followed by individuals. But earlier in the this, as you can see, this phenomena in nature are occurring for centuries. This is not a new phenomena. But in the last 50 years, people have tried to understand this. And the early papers in this field are very sometimes interesting to read, that they talk about telepathic communication between birds. They think there is a mental template of orderly movement in the brain which allows them to form this collective motion. So these things I will show you. This is not correct, but there is a very beautiful mathematical way to understand this. And this is the first attempt by a applied mathematician in 1987, Craig Reynolds, who made a very simple computer program which you can download and run it on your laptop or even mobile phone, where he said that all this flocking really occurs due to three simple rules. Number one, that the particles or the birds should have repulsion. They should avoid crowding the neighbors. Second, they should also have some attraction, which means they should steer towards average position of neighbors. And most importantly, they should align depending on the average heading of the neighbors. So this is without any leader or an overarching plan. So this program is called Boyd's. And this is downloaded from the website, that with this program, it is shown that these inanimate objects can really start behaving in a collective fashion. You can see that there is no coordination, central coordination, and when you put some obstacle, they can also break and reform. So this was a big success of this simple model, which showed that there is no top-down order required. There is no mental template of orderly flocks, and there is no telepathic communication which you need. So this is a beautiful example what Aristotle said, that you can have complexity from bottom up. Now, interestingly, after this program was made public, this has been used in many, many Hollywood movies. So when you see in a Hollywood movie, like in Batman Return or Lord of the Rings, all those scenes are created by this program. So you can really see the success of this program in Hollywood movies. So one of the fundamental emergent property of flock is collision avoidance, because people don't want to collide with each other. Birds don't want to hit each other. Now, this is very important for autonomous cars. And what has happened in the last 20, 30 years, that in artificial intelligence, the people in computer science know that there are flocking swarm algorithms. So these are the algorithms which are inspired by the flocking behavior. And for example, in this book in 1993, a lot of details are given. So first story from our lab is to understand this emergent collective behavior using not the live objects. In a physics lab, I would not like to deal with them if avoidable, but we will tell you how to make very simple models which are quite close to the realistic situation. And this is something which we have been doing for the last few years, and I'll show you what we have been learning. So this is a very simple experiment. We have a shaker which moves the platform up and down. On that platform, we put a brass, this aluminum plate, and we put these particles on this. Now these particles are something very interesting. We put a object like a bullet, which is having a head and a tail. So this is a brass bullet with length of about 4 millimeter, diameter is less than a millimeter, and we place on that. And now we shake the plate by less than a millimeter, 0.2 millimeter or 0.02 millimeter at some frequency. So the particles are jumping up and down, but the fact that these particles are asymmetric, they start moving in the horizontal direction. So this is what happens. I have just put a particle and I shake in the vertical direction. And this particle has a directed motion due to the vertical vibration. Now, if you change the particle shape, and it will behave in a different manner. It will have run and tumble motion, very similar to the E. coli bacteria. So now you can play God. You can make your own particles, your own shape, and then you can have very interesting motion of these particles, including the chiral motion when you shake the plate. So what we do is we want to understand the collective behavior. So I put many of these active rods, I call them active particles, brass rods, on the plate. And then I want to see whether there is a flocking behavior. Now what we found is that when I put only few of these rods on the plate, I do not see the collective motion which was seen by bacteria or the locusts. But then we immediately realized that there is no interaction between the particles. See, bacteria know how to communicate with each other. Birds know how to communicate with each other. Human beings know how to communicate with each other. But these brass rods do not know how to communicate. So what we did, we put raw beads, aluminum beads in between. So now the aluminum beads are interacting with the rods, and they communicate the motion of one rod with the other rod. But still we did not see collective behavior. We slightly increased the bead number, and beautifully we saw that these brass rods, the active particles, start behaving. This is a real-time movie. They start behaving in a very collective manner. And this will go on for years, as long as you vibrate the plate, which means you're feeding energy into the system. So we have recreated flocking. Now we can understand many more things about flocking. So one thing what we see that we have in a certain parameter space, no flocking, another parameter space, collective behavior, namely flocking, which we quantify with a parameter called order parameter. You can quantify that from the images. And now we can see that this behavior is not unique to one concentration on one particle. It will occur as long as you have sufficient number of beads and sufficient number of rods. So in the whole parameter space, you can get this collective behavior, and below this line, you will not get collective behavior. So there is a non-equilibrium phase transition in this parameter space. So this is similar analog of the equilibrium phase transition. Now, what is the role of the bead media? I already said, they are the eyes and ears for mediating interaction between the active particles. So they really communicate between the active particles. So now what we did when we are doing this experiment, we also plot the velocity of the beads. in addition to the velocity of the active particle. This is all by image analysis of the fast CCD images which we take. What we see is when the beads are moving in a incoherent manner, in the rods are moving incoherently, beads are also moving incoherently. But the beauty is, moment your rods show a flocking behavior, the beads also acquire an ordered motion. So this is together. So rods and beads are really communicating with each other and influencing each other's motion. For example, in these snapshots, this particular rod is very much away from the flock. This is very far away, but slowly you see that it becomes part of the flock. So what is happening is a wandering rod, this feels the motion due to beads, and beads align the other rods. So moving rod leads to bead flow, and the resulting bead flow aligns neighboring rods. So this is a feedback mechanism which introduces this collective behavior. So once we understood, we thought, let us go ahead. I'm just touching upon main results. There are many more interesting things which I will not be talking. Can we trap these active particles? And if we can, what applications we can have? So first what we did, we took these rods, put them on a plate. This is without beads, and now put a trap. This is the trap. What we found is that when the angle of the trap is less than 80 degrees, they all come together without our telling. On their own accord, they come together. But moment I make the angle 120 degrees and above, they will never get trapped. So there is a beautiful transition from no trapping to trapping at a certain critical angle. And this is something very interesting, because you can take this concept to bacteria. So for example, now, so what I'm showing is the computer simulation of the experimental results. And this is the simulation. I will not give the detail, but the result of this simulation is that if the particles have persistent motion, they will get trapped in a trap with a certain angle less than the critical angle. But if you put two of them together, then the particles which do not have persistent motion do not get trapped. And this is what happens in an experiment. So this is the experiment. We have put two kinds of particles, same size. One particle is red, other particle is blue, but they move differently when you give energy. And the beauty is that only one type of particle comes together in a trap. So this is a very unusual sieve, not depending on the size, but depending on the motion. And this can be used, hopefully, for separating the bacteria, which move differently, or the cells, which move differently. So there could be interesting application of this particle sorting depending on their activity. So now the question comes, can you disrupt a flock? Because once you have this locust which attacked the northern India in the last 2 months, question is, there the collective motion is a problem. You do not want the collective motion of the locust. So what we have recently studied and published in the time of COVID, you can see the date. What we did, Pradeep, my student, did the following experiment. He took the active rods only, no beads, at a large concentration, which form a flock. But now we take second kind of active particle, which is called dissenter. This dissenter is a black sheep. It does not obey the laws which are obeyed by the white particle. We call them dissenter. Now this dissenter, for example, in real life can be a drone, or it can be a different type of particle in the in the locus. When we put that, what we see is there is a certain concentration of dissenters which will disrupt the flock. So you can have a flock and you can disrupt it by putting decenter. So there are very interesting consequences in crowd management. When human beings are moving together and it can cause a stampede, you can put other kinds of objects, other kinds of people who will not like to follow the rule, and a very few of them can disrupt this motion. So this is some very interesting consequences which I will not go into, but these experiments open up. So let me finish this story that we see the collective behavior in many species, birds, fishes, ants, and this is what we have simulated in our experiments in the active particles in the lab. Question is it different behavior with same outcome, or there is some underlying basic rules? So I have tried to show there are basic rules, and this interaction can be long range, which can bring around this flocking behavior. So, so the summary of this is that flocking observed in nature inspires scientists cutting across different disciplines to understand this phenomena as a curiosity. But it has led to many underlying rules. And I do not say that biology is not important here. Some details can be important and we need to understand. But the beauty is the basic curiosity has led to many applications already in many areas like artificial intelligence, autonomous cars, and so on. So this is one example of interdisciplinarity where something is happening in nature. By understanding that, we have carried over to many other areas to make an impact in that field. Second example, which I will give, is a century-old problem, many centuries-old problem. This is the problem that you have a glass all around us, window glass and so on, but they crystallize over a period of time. I will show you some examples, and this is something which is not understood. So people do not want this crystallization. There are some basic problems with that. I will just show you. So this is published, those who want to know the detail, in Nature Physics 7th September, very recently, about a month back, where we have used machine learning to really predict about this devitrification. This process is called devitrification. So what is this glass? Glass, we know, this is an age-old problem, that if you suddenly cool a liquid and you avoid crystallization, you will get a glass. So it's a metastable state. But the beauty is all the atoms are disordered. They are not arranged in any ordered fashion. And the viscosity is very, very high. Now this occurs in nature, this occurs in man-made glasses and so on. Now this is something which I just thought for interesting for some of you. Glass has been used by mankind for millennia. So we found that glass making dates back to 3600 BC in Mesopotamia. So you can see how old is this problem. And this is all done by rapid cooling of liquid. Now, this glass is metastable. Now, this is a very old book which is there, which describes in detail how to make a glass. And for those who may not know, this was a state secret. All the kingdoms had this artist who will make this glass and will not tell the recipe. So they will mix various things, and the idea was how to make a stable glass, colored glass, and so on. So this has been a very much like a art and science together. Now, once it is glass, it is a metastable state. So what we find in the nature, that it tries to crystallize over a period of time because it wants to go to a stable state. For example, in opal glass in nature, people have seen that you can see these crystallites in this glass over a few hundred years. This Roman era glass in the museum has shown to devitrify over tens of years, but hundreds of years. And this is the devitrification observed in stained glass windows. You can see that it has become crystalline. And it has also occurred over obsidian, which is a volcanic glass, over millions of years. So de-vitrification happens and the time scale can vary. So why would you like to study de-vitrification? Now, I'll just give you some examples why mankind should be interested in this. And that is why we got some interest in this, which is something which is happening in the recent years. So we need to avoid de-vitrification because in many cases, like the drugs, are made into amorphous form because they are about 1,000 times more soluble than crystalline drugs. Now, people do not want drugs to become crystalline when they store in over a period of time. Then you have to avoid de-vitrification during thawing of the cryopreserved samples. Then again, in preservation of biomolecules, you have to avoid this. And this is a very important example. The nuclear waste is cast inside a borosilicate glass because you want to contain the radioactive waste. And this is buried in the ground. Now, if this host matrix, which is a glass, it becomes crystalline, it's a big problem because it will leach out radioactivity. So you would like to have stable glass which will have radioactivity built embedded into it. And very interesting example, the comets, the shape of the comet is really whether the water is amorphous in the comet or it is a crystalline ice, because the degassing depends on that. So these are some of the examples you realize have direct consequences of de-vitrification. Now, for those who are in science and biological science or physics and so on, you must have heard of this potential energy landscape. This is not a concept in one area, but it is in many, many areas. So what you do is you have a potential energy as a function of coordinates. And when you say you have a crystal, you have a potential energy landscape, which is minimum there. Now, what happens is the glass in this picture is stuck in a metastable state. Question is, how does it become a crystal? Now, this is a puzzle. Glass is a solid thing. So why should atom move to do this? Now, what we have done, I'll tell you our story. We cannot see atoms and molecules in conventional glasses. We cannot, because you cannot follow in time. They are moving too fast. So we now make a model system where the atom is replaced by a colloid. Atom is 1 angstrom in size or less. We take a colloidal particle, which is 1 micron, 1000 nanometer. This particle is a colloidal particle suspended in water, and you can see under a microscope. You can see that it will be moving. It will be having motion. We can now follow this motion as a function of time and space, because these particles also move slowly. They don't move as fast as atoms. And we can have control over size, uniformity, and so on. And the beauty is that taking these colloidal particles, we can have glassy packing of this colloidal particle or a crystalline packing. And you can get beautiful Bragg diffraction of visible light from this colloidal crystal. So we work with this colloidal glass, which are the model atoms. And this is one snapshot in a confocal microscope of these particles, polymeric particles, which are packed in a glassy fashion, disordered manner. And the color code is an artificial color code representing their different dynamics. I will not go into detail. So we can now follow these colloidal particles in real time and real space. And what we, for example, we can have 2 colloidal crystals with a grain boundary. For example, this is from our earlier work. And this grain boundary can move under shear, and we can exactly find out what is happening when the grain boundary is subjected to shear stress. So this has some very interesting engineering consequences on material strength. So the experiment is done with these colloidal particles, and we follow these colloidal particles as a function of time. So let me give you the interesting results. We can take a two-dimensional slice, which has about 10,000 particles, and our crystal has about 60,000 colloidal particles. So it is much, much more than what a simulation can do in real time. So what I want to show is the main result, because something which I thought I'll give the main message. What we find is there are two routes to crystallization. One route, which was shown in simulation, that there is a what is called avalanche route, which means nothing happens for some time, and all of a sudden some subset of particles move and they try to have a crystal. So this is called avalanche route, which we are able to capture in our experiments and show that you can see that suddenly you will have, you can see that burst of activity and things will crystallize, some particles. But also in same sample, we have another route to crystallization where we can see that these particles will move little bit smoothly and form a crystal. For example, in this video, they are moving very slowly, not in an avalanche fashion, and do that. So the summary of this last two slides is there are two routes to crystallization, avalanche route and smooth route, which was known in computer simulation in the last 2 years, but nobody has seen them in experiment. So our experiments show there are two routes, and there are very interesting rearrangements which you can understand, which you can analyze. So here I want to give 2 minutes of this new thing which we have done. Now our idea was, once we know it has a possibility of crystallization, can we predict where will crystallization occur in a glass? This is a big question. We don't know the answer. So here we use what we call, which is known for the last 15-20 years, called machine learning. So it is a supervised machine learning where we have classify the particles as soft or hard by training the system. So what we do, we have our experiment, watch over initial times and see which particles are moving, which particles are not moving. This is to train the system. We train the system to recognize hard and soft particles. So hard particles do not move and soft particles have a tendency to hop. So we train the computer system and say these are the hard and soft. And now what we do, we find out the structure around these particles, which are hard and soft. So we have the descriptors, which is a structure function around this hard particle and soft particle. In our problem, it is a 47-dimensional vector. And in this hyperspace, we can separate this hard and soft particles separated by a hyperplane. Now we can classify all the particles, not only for the training set, and we know which particles are hard and which particles are soft, just depending on their structure. We don't know dynamics information required. Now we find very beautifully that we know the soft and hard particles are separate. The red ones are the soft and the blue ones are the hard particle. What we predict is that after many days, let's say 5 days, you will have crystals which are called the white spots only where you have soft particles. So there is a prediction here, and this is the realization that the soft particle regions tend to crystallize and not the hard particles. So we can exactly know that the softness is a correct parameter to really understand crystallization. So we predict that, and machine learning helps us to identify this parameter called softness. So the message of this problem which is really very age-old problem, is can we understand devitrification? Now, our understanding as of now is that there is a parameter called softness. It is not the structure, it is not the conventional G of R, but it is much more than that. It helps to identify these two regions. Once you identify, we know that crystallites will form where you had the soft regions. Now, what is the use of it? You can ask me. Now, the point is that in the literature and in industrial applications, what we have are the empirical ways to make a glass more stable in the last 100 years or more. People put additives and they find certain additives help to make a good glass or certain annealing process. So you must have heard of this, this Corning Godzilla glass that has really learned from the machine learning is what there are some news items on that. So the point is, if you can quantify a parameter which is capable of capturing the stability of a glass, we have a big success in this field. So this is second story. Now, I have about 12 minutes left. Professor Narayan Rao, is that correct?
It's okay. It's okay. Yeah.
So I just thought the third example I will give is a bacterial heat engine. Question now we are asking is, can you make bacteria into a heat engine? Can you run a heat engine out of a bacteria? And that heat engine is a nano-size heat engine. So it's not a heat engine which you see on the platform, but this is very close to biological motors in our body. So these are the biological motors which help you to move your muscle, which help you to do everything, every function in your body. These are called the biological motors. Question is, can we mimic them? Can we learn something and make an artificial motor, artificial heat engine in the laboratory? So this is the question. So this is the work done primarily by Sudesh for his thesis, who got his degree recently. My long-term collaborator, Professor Rajesh Ganpati from JNC ASR, and my colleagues in biology department, Professor Dipankar Chatterjee and his student, Shubho Ghosh. So here I will tell you a concept which has just been proven by our experiments and lot more to do. So what we are asking, so let us go back 300 years back. 300 years back, Carnot made the heat engines. So all of us have studied heat engines because they convert heat or chemical energy into mechanical work. Now, this has changed our life, right? Because in the last 300 years, humanity is not what it was 300 years back. Huge mobility has come in. Heat engine is all over the life, not only in transport, but many ways of our life. Now, all this heat engine depends is on second law of laws of thermodynamics, which were discovered about 300 years back, or maybe around that time. So what we have in a heat engine, you have a gas and you put it in a piston and a cylinder. So you have a gas at high temperature. This gas will expand and it will do work. So the piston will move out and you will connect a flywheel. This is called isothermal expansion. Same temperature, but you are expanding. Then what you do at this time, when it has expanded enough, you make isochoric cooling, which means the volume remains the same, the temperature of the gas is reduced, and at that cold temperature, you again compress it. So the work is done only from 1 to 2, and work is not done between 3 and 4. And now you again isochoric heating, and this is called the Stirling cycle. Now in this process, you get the useful work done. That was shown by Carnot and Sterling, and you can calculate depending on hot temperature and cold temperature, you can exactly know what is the efficiency and the work done. This is all beautifully documented and proven, and our life has changed because of this heat engine. Now, what our goal is, can you reduce this heat engine to a nano size? Is this concept correct? And if you can do, can you use to transport cargo inside a cell or a microchannel? That is the long-term objective. Now, one thing we have to realize, it is not simply reducing the size of the piston and cylinder. It is not that if we have better machines to do this machining, we can reduce the piston and cylinder. It is not that. Here there is a fundamental concept. When you reduce the size of the heat engine, you will have very few particles, very few gas molecules. This will not allow you to define your temperature and pressure in a mean way. These quantities will fluctuate. So this is a very different thing when you have fluctuations in the thermodynamic quantities, which are very large fluctuation. And this has given rise to a new field in physics called stochastic thermodynamics, which means you don't work with temperature and pressure, but you work with the fluctuations of them. So fluctuations are important. This is something which we don't study in our college curriculum. This is a new concept which has come in the last few years. Now, this heat engine was made in 2012 by a German group, where they replaced the piston and cylinder by a optical trap, not mechanical. This is a laser intensity which is trapping one colloidal particle. So the beauty is the gas molecules, which were 10 raised to power 23 per centimeter cube, is all replaced by one colloidal particle. Please imagine. So one colloidal particle is trapped in this piston and cylinder, and this is doing all the work. So this was trapping at high temperature. You look at the particle motion, you expand the trap, which means you make it loose. It will do more and more excursion. This more and more excursion will do the work. Now you do the cooling of the liquid. Colloidal particle will be slowed down, and then you compress again by making the trap stiffer. This is the way they showed exact analog of the Stirling cycle. This was a big success in 2012. Now this is a microscope objective which is used to trap a particle. So it's very easy to make an optical trap in a lab. Any one of you can do it just by trapping, by focusing the light. Now what happens is, once you know the particle motion, there is a whole methodology which I will not go into, which will allow you to calculate work done and the heat and so on, and do that. Now I just want to leave a concept with you. What we asked is, can we replace two temperature baths, hot and cold, by something else so that the temperature is same, but something is different, which means in one case there is a lot of activity in the bath, other case there is no activity. So we want to replace the temperature by a quantity which we call activity. So this is something which is very, very interesting. So the experiment is the following. I think if I can explain the experiment, I'll be happy to leave without giving detail. So what we have is water with colloidal particle, which will be trapped by the laser. But now, instead of, so what we do, we also put living bacteria. The living bacteria are influencing the colloidal particle. It is making it very agitated or less agitated. So we can vary the activity of the bacteria by a slight change in temperature. Like at body temperature, bacteria is very active. Slightly at 300 Kelvin, it is not active. Now, but bacteria is still alive. So by playing with the activity of bacteria, we want to show if there is a heat engine possible. And most interestingly, it is possible. What we showed Sudesh showed that we can make exactly like a Stirling cycle where the temperature is replaced by activity. So we have large activity and less activity, large activity and less activity. If you cycle that, we can really extract the work done. And you can see that if I put the cumulative work done by this particle, which is agitated by bacteria, it really becomes about 200 times more when there are no bacteria or the bacteria is dead. So the bacteria is doing the work and particle is really making a heat engine. So this is something with various activities of bacteria. And what we show in this data, that if we plot the efficiency of the engine, we can calculate that, we can measure it. Without bacteria, it is 3%, only 3%, which agrees with thermodynamics. But now, with high activity bacteria, it becomes 50%, 0.3% to 50% because of bacteria. And it even exceeds the thermodynamic limit. So the beauty is you can make now a heat engine using bacterial activity. And this is something very exciting because it's a new concept of using some activity to make a heat engine. So this is something which we have summarized here. So I will just close my talk by asking a $1 million question whose answer I do not know. What we have shown you is a heat engine which is possible using bacteria. Now, you can always ask me, how do I connect a load to it? How do I get useful work which is good for humanity, which is good for applications? This is something which we are still working on. And it is we have to find a way to connect the load to this heat engine. So we have to devise a methodology or a new concept to connect a heat load to this heat engine. That is still something we don't know, and any of you is welcome to contribute to this challenge. So this is the summary of the third part, where we have a microscopic engine operating on active reservoir. We have realized that power and efficiency are much, much higher than the thermodynamic heat engines. And this is possible now that you can use not bacteria, but anything which can be active with light, magnetic field, and so on. So there is a lot of opportunity here. Question is, can you couple these heat engines like in your car? You have a 4-stroke heat engine, 2-stroke heat engine. Can you couple them? Recently, we have shown, yes, you can couple. And then you will have new applications in microfluidics and drug. So let me summarize my talk in the last 1 minute, that I gave 3 examples from our work to exemplify the beauty of interdisciplinarity, the beauty cutting across the boundaries. These all 3 examples have looked at some very basic problem which we think will have some interesting applications in the long run. First example, we looked at the flocking behavior, which is seen in nature all around us. But here we wanted to see how do we learn from our lab experiments. So we have a minimal model to understand this complex phenomena. We have also shown that you can disrupt the flocking by some dissenters, which can have some applications, and so on. Second example I brought in, where we use machine learning, artificial intelligence, to really predict where will crystallization occur in a glass. Now, devitrification is a very, very important technology problem. Now, question is, can we get lesson from our work and see how we can use it? And third one, which I briefly touched upon, to make a heat engine using a new concept of bacterial activity, and we showed it is possible, and you can get efficiency as much as 50 times 50% in a not 1 or 2%, and it is about 200 times more work done than without bacteria. So all these examples tell us that the key, which I can see in a very simple way, is to collaborate with experts outside our domain of expertise with an open mind. We have to have an open mind because our languages will be different to begin with. Our understanding is different, but we have to communicate and see how we appreciate each other's point. So collaboration is the key. And this brings to my collaborators in these 3 projects, which I mentioned all along. And these are the people, some of them with very different background, which has really enriched this my doing science. So my goal has been to do some exciting science and see what we can learn and train the future generation student. So it has been a lot of fun, and the fun is still going on. COVID is going on. We are all busy, but fun will not stop here. So I close my talk here, and thank you once again for having me for this lecture. And I will be happy to interact and answer any question if you have. Thank you so much.
Thank you, sir. I will request Dr. Lakshmi Narayan Patru from Department of Physics, SRM University, AP, to take care of the question and answer sessions. And please go ahead, Patru.
Thank you, sir. The first question is from Satyam Kanajaria. The question is, in just like birds, canoe humans are used flocking in daily life. Does it make it more productive? Just like birds, canoe humans use flocking in daily life.
Yeah. I showed you that human beings, when they are in a crowd and when they move together and make a stampede, it's a very, very bad example of flocking. Many million people die of stampede, and stampede is not a good thing. You know, in the Chhat festival 3 years back, there were a lot of problem. Luckily, in Kumbh Mela, people have got around to understand. And this problem, which was there at the time of in Makkah, Medina, was given to physicists actually to solve it. And you will be glad to know that the physics knowledge has helped to design the stadium and the pathways for avoiding the stampede. So this is one direct application which has been used. And there are many other examples where human stampede or human flocking is has been studied. And in many cases, if it is not desirable, people have learned from the examples. Yes.
Okay, thank you, sir. Thank you, sir. There is a second question from Chaitanya KBS. Can we replace the...
Sorry, I can't hear you. Sorry, yeah, I can't hear.
Yeah, hello, Dr. Patru. Yeah, I think maybe some problem. Murli, can you take care?
Yeah, Chaitanya is already in unmute. He can ask directly. Chaitanya?
Directly, he can ask.
Thanks. Yeah, Chaitanya, you can ask.
Yeah, I can hear you.
Yeah, great talk, Professor. I have a couple of questions. Yeah. One is that, as you said, the role of beads is to communicate between the rods. So can we replace the beads with the fluid and achieve flocking?
Yeah, interesting question. The point is the beads are able to communicate the impact of the rods and so on. The liquid will dampen the motion, and so that's the problem, because in liquid you will have enormous dissipation, which will come in your way of communicating.
So is the system more dominant in contact interactions? Like
Yes, correct.
Okay.
Answer is right. Yeah.
Okay. Next question.
Yes, sir. Next question is from Nitin Chattopadhyaya.
Yeah.
Why did you use rod-like objectives for your flocking experiments? What happens if spherical or elliptical or asymmetric objectives are taken?
Right. So let me, it's a good question. The rods actually, you have to realize what we need is a asymmetry. If there is an asymmetry in shape, it will move. If it is spherical, it will not move because it will keep on bumping there only. So you need asymmetry. So you can have asymmetry in mass, asymmetry in shape. We have used asymmetry in shape. So as long as you have asymmetry, these things will move. The beads do not move on their own because beads are not having any asymmetry. So you need asymmetry for the motion.
Thank you, sir. So there is another question for Dr. C. Subramanian. That this principle is used in formation, flight, or military aircraft. Can this phenomena be correlated to what was explained under part 1 of your lecture?
Actually, what you're saying is right. Actually, there, of course, in birds, they use this to their advantage. So what happens is, when the bird moves, they leave a wake, which is very helpful to the other birds to move, because they get helped by the hydrodynamic lift. Now, what happens is the first bird gets tired and then he comes at the back. So they cooperate with each other and actually use the flocking to their advantage, and they take advantage of this, in fact, in making a long distance flight. So answer is yes, in birds it is used already.
Sir, Murali sir, so can you unmute Professor M.B. Sankanaran, IIT Madras, so that he can ask directly?
Yeah. Yes, sir, I'm asking.
Yeah.
I'm unmuting.
Also, put the focus on him, on the participant also.
Yeah, Professor M.B. Sankanaran, IIT Madras.
Yes.
Whether he is present or not, he is not. He is present, but he is contable to some problem is there. Sir, Lakshminarayan, sir, you can take
you ask the question.
Okay. So excellent talk of immense relevance to researchers in all fields. My question is, can we employ analytical theories also to comprehend non-equilibrium phase transitions and cooperative phenomena?
Answer is yes. It is the most active field in non-equilibrium statistical physics. In fact, there is a huge community which has built up in the last 10 years in this field. So even in our paper in 2014 Nature Communication, we have given a simple model and simulation. So this is a very, very active field. And if you look at our recent work in the last 6 years, Professor Shriram Ramaswamy has done enormous amount of work in this field. And we have many things together along with experiment in some of the problems. So answer is yes, it is a very active field. And in fact, it is a field which is really having a lot of open issues. So this is something which is very good for young people, because many, many questions are unknown, answers are unknown. So this is something which is very exciting in this physics community. Answer is yes.
Thank you, sir. Sir, can you unmute Ishwarya Varla? He is having 2 queries.
He's not in the meeting actually. He can.
Okay, so I can ask, no problem. So how does the size affect flocking and trapping? I mean, can we apply micro and nanostructured materials?
Answer is yes, you can, as long as they are asymmetric. So when you take biological motors, they are in fact very small. So it will operate around on a different length scale. You need the activity either due to asymmetry or due to some biological motors or whatever you have. Answer is that it can cut across various length scales, and it is being done. Our particle is only 4 millimeter, but people have done on less than a millimeter and few micron. People have done on colloidal particles, making them active on few micron length scale. Answer is yes.
Okay, so thank you, sir. There is another question, I think, from Professor G. Rangarao. Great work, Professor Sood. do you see also flocking phenomena in cyclone?
I don't know. I don't know because these are not active particles in cyclone. Cyclone is collection of all this, air, water, whatever in a very complex formation. How much of it is coming from emergent behavior of active particle, which I talked, I don't think it is valid.
Okay, thank you, sir. There is another question from Professor P.B. Satyam. Great talk, Professor Sood, as usual. I am wondering how to handle the energetics in machine learning.
Okay, very good question, Satyam. If you are listening, see the point here is.
Yes, I am listening.
Yes, Satyam. See, the point here is the machine learning is simply you teach the machine what you want it to learn. So when we said that we taught it how to recognize soft particle and hard particle, what went into it teaching is whether the particles are hopping or not hopping. So this is one aspect in our problem. Now you can have different descriptors and different ways to do it. And if the energetics is coming in recognizing some are the two different types, so be it. In our problem, we did not look at the energetics, but we knew some particles were ready to move, some were not so comfortable. We characterized the structure around them. We understood what has to be done. And then the machine knows this and tries to classify the particles based on their descriptor. So this is a general way of doing machine learning, and it has been used in condensed matter physics for predicting new materials. So there is a huge field which to predict, let's say, new ferroelectrics, new superconductors, new semiconductors with properties which you want. So what people do, I think Ranjit Thapa can tell you more on that it will learn from the known examples of, let's say, superconductors. All that information is stored in the machine, and then it tries to make a discovery. So idea is you should have a descriptor which is able to capture the property. So there the energetics, all those things are important. So this is in fact done.
Can I just add some comment here?
Yeah.
I think many of us and many young people also should understand that from this great talk, the simplest thing is you don't need a big budget to do great science. What you need is, ideas. I always remember with you that you need to think about 1,000 ideas, couple of them work. But I think science needs a little money and more thinking and more like cross-border or interdisciplinary one.
Satyam,
I must appreciate this one.
No, Satyam, I must declare that you do need money for doing research. Okay, so that I don't think we should belittle. But point is, money, as you rightly said, is not the only thing. Money is one of the descriptors, but you need much more. And I think what you are trying to say that putting only the machines or the instruments will not do work for you, which is correct.
Exactly.
And as you rightly said, we need to think beyond that. And you do need resources. So I don't want to leave Professor Narayan Rao happy by saying that money is not needed. Money is needed for a very front-rate science, but other than money, you also need, originality and so on. So both things are needed.
Professor Ajay Sood, I agree with you.
Thank you, Ajay.
Thank you.
Professor Ajay Sood, in fact, I agree with you. I always champion for money for research.
Yes.
You might remember my talk, my speech when I gave in the presence of the Honorable Prime Minister.
Yes.
Abysmally small funding.
Yes. So money you need, but
money is needed.
I think the message which Satyam is giving that along with money, you need some thinking to see what is the best way to do it. I think both are needed. Yeah.
You are perfectly right. Just by putting machines and instruments, it will not work.
Yeah.
But at
That's
the same time, we need to realize those instruments and machines are also needed.
Yes, absolutely.
Yeah.
Cannot be said better. Yes.
Yeah. Dr. Patro,
yes.
If any last question?
Okay, we'll take the last question from our colleague, Mallikarjun Rao. I think, sir, you are there, Mallikarjun, sir? Okay, I will ask the question. Can we make an amorphous metal from polycrystalline metal?
Yes,
which is the opposite effect of crystallization to your example.
Oh yeah. This is a well-known example of metallic glass.
Yes.
So you have metallic glass, which is made by very high quenching rate, and you know that metallic glass have enormous applications. So metallic glasses are made from the polycrystalline ingots by melting and fast quenching, and that quench rate can be 10⁻13 Kelvin per second and so on, enormously large. But if you mix different kinds of metals, then you can work with even smaller quench rate. But if you want a pure metal to make a glass, you need faster quench rate. Answer is yes.
Sir, this is Mali, sir. Just I want to clarify my question slightly bit. Sir, actually, as you mentioned that with the long term, in the glass, there are some crystallization. That's what you example showed in museums and so on, right? So my question is that, like, if I can look at the metal, which was fabricated 100 years ago, do you also see some kind of a crystallization opposite effect of, because metals typically, they are in polycrystalline until unless I don't make it as a metal. As a single crystal. So the inverse effect of at the time.
No. Crystals will never become glass when you stand alone. No. So because crystal is already the equilibrium form, the most stable form. So that does not happen. But only if you have a metastable state, it will try to go to a stable state. That's the question. That's the point. So if you are left with if you are having a polycrystalline metal and leave it, nothing will happen except the structure can change from A to B. Alpha iron can form something else, is not ruled out over million years, but not really it becomes glass, never.
Okay.
Sir, I have a last question actually.
Yes.
So most of the crystallization studies on glasses, they are made by using differential scaling calorimetry. Okay, so you define the parameter softness for the study of crystallization. So what is the instrument we can find softness experimentally?
No. That's a very good question actually. So what you measure, what we are trying to say is the information of crystallization is really hidden in the structure of a glass, which is never anticipated earlier. What we are saying is that the structure has all the information. It has the full Janam Patri of the glass. This is the beauty.
Yes.
Once you know around each particle what is happening, our story of softness and hardness, which has also been done by people in glass, our story is that the structural parameter is capturing it. So that is the title of our paper. Structure determines where crystallization will occur, which is not anticipated earlier, because people think crystallization occurring because you have a lot of dynamics happening, which is correct. But structure has every information hidden. This is the answer.
Yes. Thank you, sir.
Yeah. So thank you, Dr. Lakshmi Narayan Patro. Thank you for the session, chairing the session. And I will now request, so before that, actually, I will request Dr. Balamurli, Mr. Balamurli to just show our virtual memento to Professor Ajay K Sood, which we made just today only. Dr. Balamurli, Mr. Balamurli, hello. Yeah. So this is on behalf of SRM University, Andhra Pradesh. So we want to, once you will be here really in future, we will give you a memento in really, and we want to interact with you, our faculty members, really are very excited to meet with you. Thank you, sir, for your excellent lecture. So sorry
Thank
that
you
we
so
are
much.
only projecting this virtual momento. But
No, virtual
of course,
momentum I have accepted virtually. That's
No. Physical moment also will send you physically.
Okay. So now I will request Dr. S. Mannadhan, Department of Chemistry, SRM University, Andhra Pradesh, to conclude, to give a concluding remarks.
Thank you, Professor Ranjit, and good evening to everyone. So today we have witnessed a lively and sensational lecture from our well-known, renowned scientist, Professor Ajay K Sood. Sir, you have certainly enlightened the minds of all the participants and have opened all the borders by showing new pathway to do creative science. Sir, you also have emphasized the importance of interdisciplinary research and showed the beauty of science in an exacting way. I am sure all the participants of this lecture are immensely benefited, and your talk would have rekindled their interest to extend their research in all possible direction without any limits. Sir, on behalf of SRM University AP, I thank you once again for your gracious presence and delivering such an extraordinary talk. Thank you so much, sir.
Thank you. Thank you very much.
Yeah, I also take this opportunity to thank our President, our Vice Chancellor, sir, for their constant support. And special thanks to our beloved Pro Vice Chancellor, who has been instrumental, encouraging at every point of time in organizing this University Distinguished Lecture Series. I also extend my thanks to our organizing committee members and technical staff for successful conduction of this today's session. So last but not least, I sincerely thank all the participants who are attending this lecture from different locations of our country. Thank you so much for your active participation. And before leaving, so I would like to inform you all that our next University Distinguished Lecture will be on 31st of October. So I request all to participate once again. Thank you, sir. Thank you all once again. Thank you so much.
Thank you.
Another participants from India, from Japan, from Saudi Arabia, from UK are participating. Nagoya University, Kaus Saudi Arabia, Trinity University UK are all participating. Okay, wherever the participants are sitting, let's give a big applause, thanking our beloved guest and a great scientist of this country, Professor Ajay Sood. Wherever you are, please give an applause.
Thank you very much. Thank you. Thank you, President Rao. It's such a pleasure.
Yeah.
Yeah.
So thank you very much.
We need your blessings and support for our young colleagues.
Yes, sure. Always.
Okay.
Good.
Thank you, sir.
Thank you. Thank you very much.
Thank you, sir.
So should we leave now?
Yeah.
Okay. And if you want to, I think you wanted to interact, we can do.
Yeah, correct. In between I stopped. Now, Mannadhan, you could introduce yourself and briefly tell about the work what you are doing.
No, we can say that participants can leave. Actually, So we
see what we can do is, I think what we can do is we can leave now and meet in another 5 minutes using the same link. Is that okay?
Yeah. Ranjit?
Yeah, it's also fine.
So ठीक है ना?
Yes.
See, it is now 4:30. So let us meet at 4:35.
Yeah.
Yes, sir.
Using the same link.
Okay, sir.
Yeah.
Okay.